Hello and welcome back to Differential Equations, section 3.2 on general solutions of linear equations. Now, these are going to be higher order than what we have had so far. And the part of this will also be constant coefficients, but it's not just constant coefficients. So we are going to put the theory behind this, and then for the rest of the course, we'll be learning different methods of dealing with this stuff, right? So the first two chapters, we're dealing with the first order of differential equations. The second, right now, starting from this lecture, you can have whatever order you want. So now we're going to start with the equation that says some function p of p0 of x, y to the nth derivative. This notation is the derivative notation to the nth derivative. So if you want to write the seventh derivative, you do not put 7 little tick marks. You put 7 in parentheses, right? So n to the 7 is the 7th power. N to the 7 in parentheses is the 7th derivative. Please be careful about that. We're only going with tick marks up to third derivative. So first 1 tick mark, 2 tick marks, and 3 little guys, and that's it. The rest is going to be in parentheses starting with 4 and on. All right, so then we have the next term, p1, and it's going to be the 1 derivative less. So if the first one is the 7th derivative, then the p1 term would be the 6th derivative, and so on. Plus, and then we're going to go all the way down to p to the n minus 1 of x times y prime plus pn of x times y equal to some function f of x. And again, we have homogeneous equals 0, non-homogeneous equals to not equal to 0, and so on. So the same stuff that we had before. So that's what it looks like. And again, this over here, when equals to 0, we call it homogeneous. There we go. Now, solutions. I'm going to say again superposition, which is simply means linear combination of all of these, which is the solution y of x or y of t is going to be c1 y1 plus c2 y2 plus dot 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 plus cn minus 1 yn minus 1 plus cn yn. So for the equation that is given to us, we have associated solution where the order of the derivative is equal to the number of solutions. I have to write that. So the order of the derivative order of the highest derivative equals to the number of independent solutions. So that's what we have to understand there. And we are going to have still Wronskian to check for independence of these solutions. But now the matrix is going to be really large depending on how many of these you have. If you have 7 solutions, you are looking into a matrix that has 49 entries in it. right? Because you have to list all of the derivatives going down to the 7th derivative. And solving a 7th order equation like this, you start with breaking down 7 matrix with 7 into the 7 matrix of 6, and then each one of those 6 would be 6 matrices of 5. So it starts nesting like this, and it should take you about 6 months to solve like one of these 7 order ones, which is why we don't do that. Generally, on the exam, you are asked to provide either the 2nd or the 3rd, right? And I mean, it only depends also how annoying you were in class, right? That's why you will get a 3rd one, right? If you're nicer, right, more civilized in classroom, then you get a 2nd one on the test, right?
Matrices than a sleepies. That's more matrices than a sleepies.
So the Wronskian now is going to have the y1, y2, dot, 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 all the way to yn minus 1, yn, but that's just linear, right? Then it's going to go down into y1 prime, y2 prime, dot, 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 into yn minus 1 prime, yn prime, dot, 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 all the way down to y to the nth derivative 1, y to the nth derivative 2, sorry, I lied, n minus 1, not n minus 1, because we do have original function. So n minus 1, dot, 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 all of these. And then we have y n minus 1 to the n minus first derivative, and y to the n minus first derivative of n. This matrix is going to be as large as necessary to check for independence of these solutions. And again, we have the notation where these are like absolute values. And when you have the original matrix, guys, should be like this, right? This is what they would consider a rectangular array of numbers, and it's a matrix. And you see that these are the brackets. These are not straight lines. So that's the matrix. But if you put like this means the determinant of, so you get to actually solve it. Now, these concepts are taught in linear algebra. If you didn't have linear algebra, you might not be making the distinction between these. So the top one with the brackets is a matrix that we just want to name matrix A or whatever. You can define it in a software, in a calculator, whatever. The one on the bottom is the determinant of that matrix. So technically, if I put DET, then they become the same notation, except it's much shorter to write with a straight. You will learn in linear algebra inverses of matrix, the transpose of the matrix. It's just a whole bunch of stuff that you learn. We only care about one concept with those matrices here in differential equation, and that's the determinant of the matrix, which is when you multiply, right, subtract, and you multiply the other diagonal. So that's now, as I said, for this. Those of you who took Calculus 3, you know to solve a 3x3 determinant for the cross product. And you know that you took that 3x3 and created 3 2x2s, and then each one of the 2x2s had the determinant to solve. As I said, if you have a large matrix, let's say 7x7, then you would create 7 6x6s, and each 6 one will give you 6 5x5s, right? So now you have all of them, and then each one of those 5x5s, 5, and it's like a factorial thing, but it's like those babushkas, right? You just opens another one, and then at the end you just get, your 2x2 case, which is that smallest babushka you can find, right? So that's that part. I will put it on your exam. Don't worry about it. You will see the example. Exams are not just to regurgitate. Also, it's a learning experience. So your green exam will have the rest of you all are non-green exams, but yours will
Green
have
exam, like 500 level course, right?
No, it's just a different type of paper because, I might run out the white one. We'll
thought you
have
were going
the,
for green theory.
it will have the 7th order matrix, and we'll see how that goes. I mean, the example you would like. I think that that's that, and we also have one more thing. As you can see, guys, all of this is color, right? We're defining a whole bunch of terms here. I'm now going to let's go blue for the non-homogeneous or homogeneous, whichever way you're pronouncing these things. Equations, which will have 2 parts to its solution, right? And the 2 parts that you have to its solution will be the one part we already covered, and the second part that will show up later as we go through this chapter. So, subtitle. So, these equations are the ones that have y to the n plus p1 of x, y to the n minus 1, that's the lesser derivative, then eventually pn minus 1 of x y prime plus pn of x y equals, and here it is, some f of x. This f of x is usually called either a driving term or a forcing term. And I did explain a little bit about this. You can have a kid just, going on a swing back and forth, eventually stopping, or you could be there constantly pushing in the back, which would be considered as, let's say, a sine function input. If you are to just push kid once, which could be also modeled in mathematics as impulse function, the impact function, we call it delta function, which is just one burst of energy, and that's it. It's not gonna repeat itself or anything. That also has its own solutions in differential equations and so on. So we'll eventually mention that as well. So now, when you have a non-homogeneous case, your solution is going to be consisted of 2 solutions that are put together. So you're going to first solve the case, which is the homogeneous case, and that is going to give you a general solution. And then you're going to do some method, which we will eventually learn. There is variation of parameters, undetermined coefficients, and a whole bunch of other stuff that you can use to come up with the secondary part of that solution, which will be called the complementary solution. And we are going to add those. Sorry, complementary solution is the homogeneous one, and the particular solution is the one that you add. Together they create the solution. So what does the solution look like? Solution to these things will look like y of x in this case, I guess, because we had x's everywhere up there. Is going to look like yc plus yp. Now I'm going to label this yc over here as old, meaning your ODE equals to 0, which is where you use those r's and everything else that you learned. And I'm going to label this as new, because that's when the ODE is equal to f of x. Because of equals f of x, you will have to do the extra part. And then you are going to have the overall solution to the problem. So this yc is your old solution, c1 y1 plus c2 y2 plus dot 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 cn minus 1 yn minus 1 plus cn yn. That's what I said the old one is. And the yp equals, and I'll just say, due to f of x not being 0, We'll learn this later. Because I don't want you going crazy trying to figure out how to solve this when you are not supposed to yet. I think at least 2 or 3 sections before we hit some of those solutions. And now they have you figuring out a whole bunch of these things to make sure that you understand that you can check the solutions again, you doing all these derivatives. You can compute your C1, C2, C3 if you have the initial conditions. You can check independence using the Wronskian. So there's a whole bunch of things that we can compute. We haven't done a single example. I just dumped all of these generalizations from before on a pile. They don't have you solving differential equations here at all. They give you equations, they give you solutions, and they want you to get comfortable with checking for independence and computing C's, right? So the stuff that anything but solving technically. So everything we do in DifEq is other than solving DifEq is pretty much what is in the homework.
Organizing.
Busy work, yeah. So one of the examples says, use the Wronskian to show that the 3 functions are linearly independent. So give me a problem 7 through 12. Doesn't really matter. We can differentiate. 8. So problem 8 has no coughing. Didn't we say that? F of x. We live in the times when the cough kills. So h of x equals e to the 3x. Work out the Wronskian for this. So Wronskian is going to be, and by the way, all of these problems are going to have 3 of them. They could have put one of them to have 4, but they didn't. So the first row is the row of functions provided. Second row will have the first derivative of each one of these. And the last row will have the second derivative. And as I said, if you guys had linear algebra or you guys had calculus 3 already and you know how to just fly through this and you can write the solution right here without doing any of this work, go ahead. You may also now, do other stuff, whatever. Those of you who need to pay attention, obviously, right? The way this is done is you will pick one value, and that value would kill the row and the column, and the leftover 2 by 2 is the smaller matrix that you will have to do this on. So since I am picking e to the x first, I will start with e to the x times, and then here is the matrix of 2e, 2x, 3e, 3x, 4e, 2x, 9e, 3x. And we are done with this one. Now I am going to erase my lines, and I am going to pick the next, which will delete the row and the column. Now, the biggest problem here is to remember, I guess, that you have to put a minus e to the 2x. So the first and the last term will be positive. The one in the middle will be a negative. So these signs are going plus, minus, plus. That's the way it works. Yes?
Could you just cross product the y prime and y double prime, and then dot product the It's the original one.
Yes, but again, I can see the calc 3 seeping, right?
Do you have to choose e to the 2x, or can you choose anything in the column? Like, can you also choose 2e to the 2x?
You can go either, yeah. You can do it anywhere. It's just harder to, in my never humble opinion, right? It's harder to see because now I'm creating another matrix here, e to the x, e to the x. You can literally pick any value. You can go along any row, any column. It's just the rest of the matrix needs to be in here. But yeah. Because the matrix is a rectangular array of numbers, and you and I might just arrange the matrix differently, but we must have the same solution at the end. So the second one, and finally, the third one will be that and that. So plus e to the 3x, and we have whatever is not crossed out is the matrix, so e to the x, 2e, 2x, and 4e, 2x. I will strongly recommend you practice this with something like 1, 2, 3, 4, 5, 6, 7, 8, and 9 before you go writing these infinite amount of e's, ln's, and sines and cosines they have in a book. So run a couple of these with random numbers, and you can check this in Wolfram Alpha and mathematical software, and it will tell you the number at the end. So, MATLAB will do it, and Mike can write a code as well to check the validity of your Vronskin as well. So that's next.
Out of curiosity, say you were doing something slightly larger than that, how would you go about that? Because I've only ever done a 3x3.
I'm sorry?
You just break out to another coefficient in the front for each of them.
Okay. Oh,
Yeah,
really?
it'll be like whatever the top row is times, say if you're
So
doing
then
4
E
by
of X
4, it'll be that times the 3 by 3.
With
And
the
then
2
you
by
do all
2
the
on the end.
determines.
And then each one
it's
3
a
by
train
3 will
wreck.
be broken this way.
It's a train
It's
wreck.
nested. It's nested.
Oh,
So
Like
you are
the-
times.
Yeah.
Yeah. It's not doubling the amount of work. It's exponentially. Yes.
Like I said, it's a train wreck.
All right. So now we have in each one of these, right? We have these guys to follow,
Okay.
and then hopefully everything at the end ends up on a pile. And again, if it's a 0, we have dependence. If it's not a 0, they are independent, and we're good to go.
The first two cancel out, and the last one is 2e to the 6x.
So you said the first two are canceling out,
Yeah, they both end up being 6e to the 6x.
but you have 18, right? This is e to the x times, and you have 18
e to the 5x.
e to the 5x
12.
minus 12 e to the 5x. So it's, oh, you mean it will cancel with
Yeah.
whatever the second one works out to be,
Yeah.
which is 9e
To the 4x. Minus 3e to the 4x.
4x. Beautiful. Oh, these are parentheses.
Yeah.
And then we have plus e to the 3x times
4e to the 3x minus 2e to the 3x.
There we go. Thank you. So now the first one is a 6e to the 6x minus 6e to the 6x plus this is a 2e to the 6x, and together is 2e to the 6x, which is not 0, independent. That's a very lousy example question, but it's an exam question, right? Why do I say lousy? You're checking for independence of solutions. So
That's it. We don't have to do anything else.
for this particular case, yeah. Now we're going to take a look at another situation. A third order homogeneous linear equations are 3 linearly independent solutions are given. Find a particular solution satisfying the given equation. So give me a problem 13 through 20. disqualified.
Pretest.
Well, I would choose 15, but also
15.
We have time. There's time.
We are not going to go into the next lecture, so yeah. So now we have y. They don't go with the 3 tick marks, they go immediately with parentheses. I have no issues if you go this. It's still easy with 3, but with 4 it's becoming already annoying. 3y double prime plus 3y prime minus y equals to 0. And here are they. Y of 0 is 2. Y prime of 0 is 0. And y double prime of 0 is 0. Now, they're also giving you that y1 is equal to e to the x. y2 is equal to x e to the x. And y3 is equal to x squared e to the x. Well, we kind of see that because that on top factors to r minus 1 cubed, which is going to give you r equals 1 as a triple root. We could have solved this because it was factorable and easy. But that's okay. They're really nice in this book, right? Consider it. So y to the x is equal to c1 e to the x plus c2 x e to the x plus c3x squared e to the x. Now this is what we would call general solution, which we are going to push further because we have the conditions given. Now we know we need y prime and we need to know y double prime, and we are so not gonna make it. Why?
Wait, because if y to 0 equals 0, then it's just c1 equals 2.
Yeah, but what is the issue with the rest? We have to use what?
Because if you put in like 0 for x, which is outside of the exponent, you're just going multiplying it by 0.
Well, c1 equals
Oh, then that's cool, but we still have to use y prime and y double prime to find c2 and c3. Why are we not gonna make it?
Because C.
Because the derivative. Anyone?
Oh, it's you get the x.
product rule.
Product rule. How many product rules are you gonna have? Well, 2 right now, which is gonna have 5 terms, but then in the second time around, you're gonna have more of them. So yeah, I forgot to tell you to turn your notebook sideways now. Oh, he quit.
I have work.
All right, so c1 e to the x plus c2 times, and here is your product rule. Copy the first, derivative of the second, plus c3. Copy the first, derivative of the second, plus second derivative of the first. So now we see that our y prime of x is c1 e to the x plus c2x e to the x plus c2 e to the x plus c3x squared e to the x plus 2c3x e to the x. And that's just our first derivative. Second derivative will have a product rule here, and product rule here. Yeah. Right? So it's not hard. It's annoying. It has a difference between the two, right? So now y double prime of x is equal to c1 e to the x plus c2 product rule. Copy the first derivative of the second plus copy the second derivative of the first plus derivative of e to the x is e to the x plus product rule again, c3. Copy the first derivative of the second plus copy the second derivative of the first plus 2c3. Copy the first derivative of the second plus derivative of the second, copy the first. There you go. Now we get to plug in values. into D's. So I will label this equation 1, equation 2, and equation 3. And equation 1, my condition was, you said 15, right? That's what yes. So y of 0 is 2. So 2 equals C1 e to the 0, 0, 0. Good. Second equation, y of 0 is 0. So 0 equals C1 plus C2. Everything else is 0. And the third equation, y double prime 0, 0. So 0 equals C1 plus C2 plus another C2 plus C3 is gone, 2C3. There we go. So here are our equations. We're able to do this going 2 minutes over. That's great. So C1 is 2. That means that the C2 must be negative 2, so they can add to 0. And now from the third equation we have 0 is equal to C1 is 2. C2, that's going to negative 4 plus 2 C3.
Just gonna be 1.
So C3 is 1. And we get to write the solution now because we have it. Y of x is equal to 2 times e to the x minus 2 times x e to the x plus x squared e to the x. And if you want to flex a little bit, because you can, you factor out e to the x, and you're left with x squared minus 2x plus 2. And that would be what we call particular solution, because we don't have any c's left over around. Yep, bye.